You're listening to Cultivation Elevated, hosted by Michael Williamson and Anders Peterson, where we discuss vertical farming and the future of cannabis and food production.
Hey, what's going on, everyone? From Pip Horticulture, I'm Michael Williamson along with Anders Peterson, and you are listening to Cultivation Elevated, the podcast where we dive into all things cannabis, food crops, CEA, and vertical farming. Today, we're going to be talking about a topic that probably should be talked about more often. We're going to talk about airflow mapping and quantification today.
First of all, it's a topic I love talking about in terms of airflow and climate control, especially pertaining to vertical farms and multi-tiered mobile systems. But it also came up between you and me in natural way this week as we were talking about a project you're working on, and it seemed like a good topic to bring up on the podcast. What are you going to be doing with airflow mapping coming up? And why did this
Yeah,
whole
so
start?
Yeah, I'm working on a startup, and we're about actually at the 1 year marker. And so, I really think about commissioning the building and commissioning the team and getting things somewhat dialed in as, ideally I'd love to say I could do all that in 6 months, but it does typically takes about a year or so to really
Mhm.
get everything kind of harmonious. And we've dialed in pretty much everything else. And the one outstanding area that we have room to improve upon is the consistency of the airflow through our canopy, throughout the cube of the rack, if you will, and that's at every layer. And so when I reached out to you last week or earlier this week and said, hey, I'm going to be doing some airflow mapping, are there any other like KPIs that I should be measuring in addition to airspeed or velocity? Like leaf temperature we talked about as well. I was almost curious if I should even be probing some of my substrates and looking at like water content. But anyways, that's kind of what stirred some of this. And yeah, I just, people talk about like, oh, I'm going to add a fan. I'm going to add a fan here. I'm going to add a fan there. Well, that's all fine and dandy, but I really believe in that saying, if you can't measure it, you can't manage it. And so before my team starts to just add fans in places they feel like there is low airflow, I really just wanted to map it out and quantify it. And so my intention was to basically take a reading at every 4x8 tray and at a very consistent elevation, which we'll talk a little bit more on how to set that up. And so that I could just basically we could look at it together and say, okay, here's where we're looking really uniform, and here's where we're not looking really uniform. And so that way, when we do go to add fans, remove fans, increase airflow, or make any kind of adjustments, it's based off of something that was quantified.
And I think that's so pertinent to a lot of other growers out there listening. Like this topic is not, you're not alone in that, right? And that's why I think it's important to talk about. Because airflow affects so many things. I like to think of it as the great equalizer amongst a lot of the cultivation parameters. Dr. Bruce Bugbee, he talks about nine cardinal parameters of plant growth and airflow being one of them. But really, when you think about how these growers operate in terms of an energy balance, airflow really can be an equalizer amongst all of these things. And also think of it this way. If you have all of your parameters dialed in but uneven airflow, it's hard to actually optimize everything else too, because you're losing consistency amongst your growth rates, your crops, even plant heights, yields, everything. And so I do have quite a lot of growers coming to me asking like, "Oh, I want to improve my airflow or I want to add fans." I like to call them Band-Aid fans after the fact, of you've walked
Hmm.
into grow rooms and seen fans pointed every which direction, based on a lot of visual observations by the growers and the team in the facility thinking this is an area of a dead spot. Let's put a fan here. But you're right. I think the best way before you start installing fans or adjusting your airflow devices within the grow room is to quantify what you're currently getting and creating a sort of airflow map of your canopy across both tiers in a multi-tiered room and really using that data to inform any retrofits or renovations you're doing to your in-room airflow, whether that's in rack or fans above or in front of behind the racks, etc. And so there's a lot of things you can do to quantify that. In general, too, it's always interesting to me with the advent of all of these automation and control systems, these cloud-based data collection and monitoring platforms for growers. There's a lot of parameters being tracked, but I never see airflow for indoor cultivation facilities being continually tracked, in a 24/7, 365 way. And there are some technical reasons to that. And I think we're getting closer and closer to bridging that gap with better sensor technology, lower cost sensor technology, um, that will ultimately, I think, change that landscape moving forward. Um, for example, I'm installing continual 24/7 airflow sensors in a research trial that we're doing with PIP and the Cannabis Research Coalition, Dr. Allison Justice. We went down the rabbit hole trying to find all the available options out there for integrating an airflow sensor into a canopy, into a 24/7 continual data monitor. And there weren't a lot of options. And that's what I'm really hoping these kind of conversations will change is, you know, it'll get people to start developing more options and better quality sensors. Um,
So
but yeah,
before we go too deep, maybe let's talk about what are some of the results when you have poor, inadequate airflow for people who aren't as familiar, who haven't worked in a commercial space yet. And what does it look like when you have too much airflow as well? Um,
yeah,
so historically, when we see inadequate or low airflow, there's a bunch of different things that kind of happen, and one of the things could be, you have what people commonly refer to as a hot spot. And hot spots sound just as they're named. Maybe the temperature is warmer in that area. And sometimes you can even feel it as a human being, but as a plant, you can physically measure it by taking leaf surface temperatures and recording. So it's a nice quantifiable way. But typically, when we see hotspots, sometimes those plants might dry back faster, different than maybe the rest of the plants. And if the substrate sensor is located in a hotspot area, it could be throwing off a lot of the crop steering techniques that you're using for the rest of the room. Or if it's not in that area, it's negatively impacting that plant as well. Um, the other thing that we typically see is sometimes bud structure will not be as desirable or uniform or as dense. Sometimes we
hmm
get a lot of stretching of plants depending on what stage they're in. Sometimes the actual buds themselves, they start to kind of stretch as well. They'll foxtail, as people will call it. And then, as you get into later stages, if you have high heat or maybe even stagnant high humidity, you can deal with things like botrytis as well. So, there's a handful of different things that can negatively happen when you have hot spots. Are there any other things that come to your mind, Anders?
Yeah, oftentimes, when you're not getting adequate airflow through the canopy, the plant is producing oxygen, right, via photosynthesis and wants to take in CO2. But when the air around the boundary layer of the leaf is still, uh, that oxygen has nowhere, it's not being replenished with fresh CO2 and the oxygen being moved away from the stomata. And so you get essentially a localized area of poor VPD. You have either typically too low of a vapor pressure deficit to get that plant to transpire. And so visually, sometimes that can represent itself as what looks like a calcium deficiency in the upper parts of your plants, because there's very little transpiration occurring at that leaf surface. You get that yellowing towards the top of the plant because calcium is an immobile nutrient. And so, with lack of transpiration, you get less translocation of calcium to the upper portions of the newer growth of the plant, and you start to see yellowing or calcium deficiency symptoms. Oftentimes, growers see that and supplement with higher calcium in their feed, but that feed cannot get to that upper part of the plant if the VPD does not pull it like you're drinking through a straw, with a vapor pressure deficit. So oftentimes that can be a result too, is what represents as a calcium deficiency. When I see that, it's typically telling me there's something wrong with the VPD, either the temp and humidity combination, and also with the airflow. So
That's a really interesting comment because, if you kind of think back of all the different visits and growers you've talked to, or like, hey, I'm seeing this, looks like a CalMag. I mean, it's one of the easiest things that comes out of people's mouth as like, this is a CalMag deficiency. But I don't hear people saying like, oh, this is like a microclimate issue. This is a low VPD, low evapotranspiration issue, which is causing this.
Yeah.
So it seems like there's a decent amount of education around that. I got a feeling that a lot of people are not dealing with low cal mag issues in the first place.
I agree. And to the points you made too, right? Like oftentimes you'll see, even with running like a monocrop of the same cultivar, you'll see varying plant heights. Oftentimes I see it in the corners of rooms or sometimes in the back
The
where
back.
the
Yeah.
height of the plant starts to increase in the corners or towards the back, caused by those microclimates, lack of airflow, um, and you'll end up seeing that plant stretch. And all of this will, to simplify it, reduces quality and yield. So you're leaving yield on the table by not focusing on these climate parameters like VPD and airflow. But assuming you have the climate well controlled, airflow would then be the culprit, and it's oftentimes an easier parameter to retrofit or address after installation and startup than climate, because as we all know, HVAC and dehumidification retrofits can be quite challenging, but airflow retrofits are somewhat simpler to do.
Yeah, that's
So,
fair.
um, so yeah, I mean, how do we do it? Right? I would say the first piece of advice is avoid it in the first place in your room design, right? So by again paying more attention to your mechanical system's capacity and sizing, how it's sized for your room, and then how that capacity of your mechanical system is distributed throughout the room in terms of supply and return ductwork, the right diffuser selections to make sure you have that air from the ductwork throwing to the right places, and then making sure that mechanical system works in synergy with any in-room air devices like vertical air solutions and rack airflow. Um,
Hey,
one
real
thing you
quick,
can do,
what happens when there's too much airflow? Because we talked about when there's too little
oh
airflow, but
yeah,
can you highlight some of the kind of challenges that come with, having excess airflow?
yeah. So kind of like over and under watering, you get kind of some of the same symptoms, but in this case, you've sped up transpiration so much with too much of airflow that you're pulling too much nutrients up to certain plants. Sometimes you can get toxicities of nutrients in parts of your plant. Also, you're now just drinking so much, your plants are drinking so much more water because there's so much more of an airspeed growing across that leaf surface and the stomata that now you'll start to see just a higher watering rate in the entire room, which can lead to plant health issues as well. Oftentimes, you start to see quite like a wrinkly, like wind burn on the leaves that are being exposed to too much of an airspeed. And then you'll see it in the root zone sensors too. You'll see your dryback rates going so fast that it's hard to maintain your irrigation strategy and balance that system. So it just throws things out of balance.
Hmm.
Both
Nice.
can be deleterious to your yield and quality. But what I was saying is to solve the problem before you even get up and running, there are options to do things like airflow mapping in a grow room in a computer simulation prior to building it. There, I would say quite a bit of barriers to doing that and technical challenges. So it's not practical, I think, for everyone to be able to do what's called CFD modeling in a grow room. It stands for computational fluid dynamics. Essentially, it's a 3D model you build of your grow room and you assign and you basically turn on your equipment digitally and see how it runs in your room before you build it. And then have the opportunity to adjust your design, say ductwork, fans, whatever, prior to buying that equipment and installing it to see if you can improve the airflow distribution and climate distribution through your space. Um, I've seen it done on a bunch of projects. I've seen it help quite a bit. It's also quite cost prohibitive to some people, so it's not practical, right? So that's really one of the main things you can do prior to startup is do airflow mapping and then spend a lot of time with your engineers and growers to design a room that functions well.
And if you were going to do this, because, you say it's expensive, but it's also really expensive to have low yield and crop loss and deal with botrytis. And when you start to like calculate the true cost of what risk you're mitigating, it's not that expensive in scheme of things. And the other thing that's
It's
worth
fair.
mentioning is if you're gonna, let's say you're on a budget, but you're like, I really got to do this. The nice thing is you're probably predominantly going to focus on this in the flowering rooms.
Hmm.
And you don't need to do all, if your rooms are all uniform, you really in your HVAC is all uniform and consistent. You don't have to do it for all the rooms. You could just do it for one of the rooms as an example and get close enough with everything else.
Yeah, I mean, cost wise, if you hire a third party engineering firm that specializes in CFD modeling, because it's quite complex software, you can't just download it on the internet and try and figure it out yourself. You'll ultimately get a result that is not accurate to reality, right? Because just because you can generate a model doesn't mean that model is accurate.
Mhm.
So that's a big issue I've seen is people generate a model that means nothing because it was set up in the wrong way. It's a giant math problem. It's based on what's called Navier-Stokes equations. And so, but cost-wise, you're looking at anywhere between $8,000 to $15,000 for a model like this.
Not bad. Yeah, I was
Yeah.
going to guess like 20 plus. I know we spent a ton of money at PIP when we were doing the VAS kind of 2.0 Gen 2 because we
Mhm.
really wanted to be sure about the data that we were putting out and make sure that it was going to exceed the needs for most growers.
We
But
ultimately brought that in-house for product development purposes. We don't typically do full room models. We're typically modeling airflow through ductwork, through fans, into our
for
racking. Yeah.
yep, makes sense. So yeah, I mean, honestly, for let's say sub $20,000 and you've got a multi-million dollar project, you're spending a couple $1 million on HVAC. And if you can de-risk your situation and have to have less of a dialing in process or commissioning process, that seems like a pretty worthwhile investment, just listening to it for the first time.
I would agree. If I was building a brand new grow from scratch today, I'd budget that into my, build out costs. It just saves so much time and money in the long run.
So we talked about airflow mapping early on, but I guess let's highlight a little bit about what that is in different approaches on how you can do that. And because I'm doing this next week, I actually just took my PIP drawings that I
Hmm.
have because PIP does all these free layouts for customers. So I took our PIP drawings, which so I have a layout of every single room where I have multiple tiers. I'm basically just creating a second map so
Hmm.
that I know this copy is tier two and this is tier one. And I just put a little overlay where I have like a text box where I can put for each tray, essentially I can click on it really quickly and I can type in here's the data I want. You could also obviously write this in. I just didn't want to do it twice. And I wanted to be able to hand my team like a quick deliverable and say like, here's a quick visual aid. Let's have a discussion around it. Let's have a
Hmm.
discussion around our approach. But how would you recommend someone mapping out their facility if they don't have a PIP drawing to kind of work off of?
We'll start with a benching layout, a basic sketch of your room from a top-down view with all of your bench layout, so your racks. And again, doing that across every tier in a multi-tiered room. So you start there with your airflow map. I guess you could also do it. I've seen people do it on a spreadsheet too, where they have numbered their rows
Mm.
A, B, C, one, two, three, that kind of thing. And then they're following a system. On a spreadsheet, input the data. For example, I've seen people use a benching layout where all that is a template for the naming conventions. Row A, B, C, D, E, and table one, two, three. So you're looking at table 1A, row A, table one,
Hmm.
right? To come up with some sort of naming convention and then essentially follow that as you're inputting it into a spreadsheet of all the data you collect. So we do it that way. I like building out table layouts kind of in a spreadsheet. So as I enter data, the data I've entered in the spreadsheet represents where it is in the racking layout because once I have all the data values, then I can assign color ranges to the numbers that I've collected, and I can start identifying blue, green, red, yellow spots, right? So you
Sure.
can, use data validation in Excel to start color coding the data you collected automatically based on your preset acceptable ranges of those values. So it creates a heat map, a visual and a
Yeah, it's a nice
numerical heat
visual
map.
aid. Yep.
Yep. So I've done it where I've used outlining in Excel to create my benching layout, right? And just resize the boxes. So I have an Excel-based version of my racking layout. And then just put in all the formulas for, 78 degrees is going to be in the range of this color, whatever it is, right?
So the
If
cool
you're
thing
doing,
is I'm hearing is anybody can do this. You don't, you can go from as simple as drawing boxes by hand of a room and just hand writing them in while you're taking a handheld measurement on like a more of a primitive level. Or you can get really complex and really, go deep into Excel and, create not only tangible data that can be manipulated, but it can also be shown in a visual way, and mapped visually. So it's really easy to see like, here's the red hot spots in these rooms.
Hmm.
Um, okay. And so I guess let's talk a little bit about if we kind of understand generally, different approaches to mapping. Um, and also what I heard is it doesn't cost a whole lot of money to create a map.
No, it takes time.
Yeah, that's fair. So now once we've created some version of our map, can you highlight a little bit about what frequency or cadence you're taking samples? And maybe we should also back up and talk about maybe some of the tools we're using and
Hmm.
what KPIs we're measuring specifically.
Yeah. So let's talk about what is realistic with the tools available today, right? And what most growers could easily purchase, on a budget or, realistically today, right? Because there's the advanced way of doing it, and then there's the way that most growers are going to be able to do it. Um, there's indirect and direct methods of creating these maps, right? So a direct method would be using an airflow sensor, a sensor designed for measuring air velocity, and capturing direct airflow data. And we'll dive deeper into that, the different tools there. But also, just quickly, the indirect method would be using leaf surface temperature as a proxy for airflow. Um, I would collect both at a minimum. So you're collecting actual airflow data and you're collecting leaf surface temperature data. At a minimum, that's the two that I would take. I would also note plant height when
Mm.
taking this data. Um, And if you have your racking layout, it also makes sense to know what your spacing from your tray to your lights is and how dense that canopy is.
Would maturation time be of any relevance in this as well?
I would absolutely take into account how far along you are into the cycle,
Okay.
you know.
So um, we have airflow, we have leaf surface temperature, we have plant height, and then we have like maturation.
Yeah, at a
Okay.
minimum, that's what I would do. And so maturation time is pretty simple. Plant height is pretty straightforward. Um, and let's start with direct measurement of airflow with an airflow sensor. So before we get into how you do it, there's quite a few different airflow sensors types out there, and there's some that you should avoid. One you should avoid is what's called a vane anemometer. You've probably seen them with a little fan that spins, and the revolutions per minute, or which the speed at which that fan spins, correlates to the speed of the air, right?
Mm-hmm.
I often see growers wanting to use these. Unfortunately, they're not the right tool for the job. They're not sensitive enough for the low air velocities that we're trying to measure in indoor cultivation. They can't accurately maintain those low air speeds. They're meant for much higher air speeds and air volumes. So
This
I
would be
would
something you
avoid
could find at
those.
like Home Depot or Lowe's. They're like 30-ish dollars. But that is probably one of them. When I talk to people about measuring airflow and they bring out a device, 90% of the time it's a vane anemometer.
Yes, that is because that's the most easily available one, and it's easy to get your head around how it works. So when you go on
Mm-hmm.
Amazon, you look for airflow sensor, you're going to look at vane anemometers. Oftentimes they're used for weathermen and they're used for hunters, for ballistic calculators for shooting. They're used for a whole number of reasons outdoors on top of a hill where you're getting mile per hour readings. That's just too much for a lot of what we're doing. Instead, there's a much more sensitive tool called a hot wire anemometer. It looks like a little stick. Oh, yeah, you got one right there.
Go on here, got the box.
Yep. And so a hot wire works a little bit differently, but it is a better tool for the air velocities that we're targeting in indoor cultivation. There's a little wire that is heated up by a voltage. There you go, and that little bead right there. And it's a very small little probe. And that's what's called a unidirectional anemometer. If you look on the tip of that too, there's an arrow, which
Mm-hmm.
denotes the direction of airflow. You want to be
Yep.
cautious of that. These are often used in the HVAC and ductwork industries. They're used to measure flow within ductwork, to calculate CFM, to validate your HVAC design, or to figure out obstructions or clogged filters, etc. A number of reasons they're used. But they're meant to be able to be much more stable and accurate at lower air velocities in the 0 to, 1,000 feet per minute, right? So most of the airflow we're taking at the top of a canopy is going to be between 0 and 300 feet per minute, right? And so that's feet per minute, right? So that is a pretty low air speed, and that tool is sensitive enough to create and measure a reading there. Um, and that's why it should most commonly be used. Um, but yeah, that little bead is heated up by a voltage, and then as airflow goes across that hot wire and cools it down, the voltage required to heat it back up to set point correlates to the amount of air velocity going across that hot wire. That's how it actually works. Um, that is the tool I would recommend buying. They're fairly cost effective. I
I
like
think what, $125 ish sound
Yeah,
right?
like that one that you pointed out there. I think that's called the Testo 405i, I
Yep.
believe. It's a
Yep.
Bluetooth anemometer with an app on your phone, a lot of great visualization tools. I've used it. It's a cheaper sensor, and so what happens is if you expose that one to too high velocity for too long, it loses calibration. I've invested in some nicer ones. I've probably tested out, I don't know, 10 or 15 of these different sensors over the years. I do like a lot from the company called Field Piece. I have one I think called gosh, I forget, STA 12 or something like that, but it's a Field Piece hot wire anemometer. That one's more like $500 or $600, but it's much more accurate and the calibration lasts a lot longer. So I like that one. It does average functions, max, min, all that kind of stuff.
Mm-hmm.
Um, so one thing about hot wires, and when I talked earlier about technology needing to advance, is while it's the best technology, the most cost-effective and most accurate technology for measuring this, it's a unidirectional measurement. So when you're measuring on the canopy, say you have a horizontal airflow pattern, you need to make sure you orient that probe in the direction of the airflow, right? If you're in a vertical environment with air blowing down on your canopy, you need to orient that probe in the direction of the airflow,
Mm-hmm.
okay, to capture that direction of flow. There's another kind of hot wire called an omnidirectional hot wire anemometer. That would be a much better tool. The problem is they're just not typically available in these handheld lower cost solutions because they're not typically used by HVAC contractors. They're used for more specialty applications. That's what I've installed in our research chambers is omnidirectional hot wire anemometers. And
Do you
we've
remember
been
the
able,
brand on that, just for our listeners who are like ready to go
there,
down the rabbit hole?
Yeah, and you could create your own handheld version of this by buying a data logger and hooking it up. But so a few companies that make the omnidirectional ones is TSI Alnor. They make an airflow transducer, which is what one of these is, and then Degree Controls. They're a company that also makes a hot wire anemometer. Ultimately, that's the brand that I used. They had installed these in cultivation facilities. They were able to build me some custom electronics in it to integrate into companies like GrowLink, Rhythm, Priva, all of that. So they gave me a
Nice.
4 to 20 milliamp output. So that would be a great solution too, is an omnidirectional hot wire. But I've been using unidirectional hot wires for many years, and that data is still very useful and very valuable. In practice, the way you go about using it is you find it's important that that sensor is stable. I've used things like microphone stands, or I've built my own PVC stands where I've actually mounted that probe on a stand at an adjust. I like the microphone stand because you can adjust the height to the height of the canopy.
Okay.
But the more stable that sensor is, the more accurate it is.
And
Um,
if you're taking readings, you want to be taking readings as consistently as possible when you're mapping a room. So building almost like the equivalent of like a jig
mhm.
is going to be important as well. You depending on, just a couple inches, too high or too low can skew that data quite a bit.
That's right. And you essentially want to look at the height of your canopy and kind of create a best fit line, right? Like what is the height of my canopy in general, and take those measurements all along that horizontal line of that canopy height. Usually, I think if you do like because it can be time consuming, I'll do a minimum of like two measurements per 4x8 tray, one every 4 feet. Essentially,
Okay.
I'll take a measurement. Can you do less than that? Absolutely. That's just what I like to do in terms of data collection frequency, especially with a stand. You can get through that pretty quickly. Um, and so yeah, I'll do one every 4 feet, and I'll record the average and the max typically out of that tool. One important thing is airflow is variable, right? There's no perfect laminar airflow in a grow room, so it can be turbulent. So the average is really useful because I will sit there and I'll take a minimum of a 30-second recording when I take these airflow readings so that you have an ability to get a true average. Sometimes I'll let the recording go as long as a minute and a half, 90 seconds, if I'm having trouble getting a good reading. Um, there's a lot of reasons why you might find a dead spot, but you got to kind of play around and find the location, get a good reading.
Yeah, that makes sense. Now, you highlighted something for me that I think everyone should know as well. There's certain times of your photo period that you want to be taking these measurements, and there's certain times where you don't want to be taking these measurements. They're kind of bookends. You want to highlight that a bit?
Well, for the air velocity readings, because what you're going to be recording is feet per minute velocity, and you're going to be taking them, at every 4 feet or every 8 feet on all of your room. And then you can have the average per row, per tier, the average for your whole room. You can use that data to start mapping out dead spots and spots of higher velocity, etc. The photo period doesn't matter as much for the air velocity as it does for
The
the
leaf temp.
leaf surface temperature readings, which is the next one we can go on to if you don't have any.
Yeah. No, I think it's a good transition. It's important.
Yeah. So the other way to then back up this airflow data, and it's just a useful parameter you should be measuring regardless of airflow, is leaf surface temperature. But it can be sort of an indirect measurement for airflow too. When your airspeed, you can experience, you can identify in the room if you're taking leaf surface temperature on average what most of your room leaf surface temperature is. When you start identifying outlier areas where your leaf surface temperature is typically a lot higher than the rest of the room, that can typically or sometimes mean that is also a dead spot for airflow. There's a couple reasons why your leaf surface temperature might be higher in that area, but it identifies the areas where there's something going on for you to, investigate further. Like for example, you could do the leaf surface temperature readings first and then spend more of your time taking airflow readings in those areas at a higher data collection granularity
Mm.
than the
Hmm.
rest of your room to really understand if that leaf surface temperature rise is due to airflow or another plant health concern. So
Nice.
it helps you minimize error, I guess, and troubleshoot the problem. But leaf surface temperature is quite interesting. It's of quite a useful tool, and plus it can be useful in your VPD calculations to make your VPD calculations more useful. That measurement, though, ideally should be taken in the middle of your photo period.
So yeah, not too early in the photo period and not too late in the day. We want to make
Yeah.
sure that we have like active transpiration happening.
Yeah. So if you start taking leaf surface temperature readings, to understand how your plants are performing and to correlate it with your airflow data, if you take it right after the lights turn on, your plants haven't woken up and started transpiring yet. And so your leaf surface temperatures typically will start to drop as your plants wake up and start transpiring. So you'll start to see them go down. And same thing with, the golden rule of irrigation, transpiration before irrigation. That's one way of timing your P1 shots too. That's maybe a side note, but
Hmm.
um, so anyways, as plants start to transpire, they evaporatively cool, just like we feel cold when we sweat and air blows across us. Plants' leaves do the same. As they start transpiring water vapor, um, the leaf surface temperature drops because of that evaporative cooling effect. And so that's why your leaf surface temperature is typically lower than your ambient temperature in a healthy room with healthy plants. Taking those readings in the middle of the photo period gives your room a chance to stabilize. Your plants have woken up, they're already transpiring. You now already have that offset from ambient to leaf surface temperature, and there's less things affecting that data. It's a more unbiased time of the day to collect that data. Same thing at
Let's
the end of
talk,
the
let's talk
day.
about the tools on that too, as well. Because again, I think a lot of people go to their local hardware store and grab like a temperature gun that's not necessarily, again, like in that 30-ish dollar range, is not necessarily the best tool to be using to take leaf surface temperatures.
Yeah, so that's commonly what you see is you see people who want to measure leaf surface temperature go to Home Depot or Lowe's and buy an IR thermometer, which is what those temperature guns are, an infrared thermometer. That's a non-contact infrared thermometer from a hardware store. The problem is those um, a lot of the ones you buy at Home Depot or Lowe's are calibrated for drywall to detect things like termite damage behind a wall or broken pipes or a number of different issues around your home. IR thermometers work off a concept called emissivity. And emissivity is a scale of 0 to 1. And it's basically a material's ability to absorb and reflect radiation. And so all different material types, aluminum to leaf surface, like plant tissue, have different rates of emissivity. What you want is a non-contact infrared thermometer that has adjustable emissivity. It allows you to change it on that 0 to 1 scale. Most plant leaf surface tissues have an emissivity value of 0.95 to 0.97. To be honest with you, the study hasn't been done exactly in that range what cannabis should be. Most people think based on other crops and leaf types, it's closer to the 0.97 emissivity setting to get, and that what that does is that means that the temperature your IR gun is giving you is more accurate. Because if you have your emissivity set at zero point 0.2, you're going to be degrees off of the actual
Hmm.
temperature of that leaf surface temperature. So it's going to be telling you the wrong data. Um, so I use 0.97 on mine. I have an adjustable one. It's a Fluke 62 Max, I believe, is the one I use. About $100. I buy it on Amazon. And some best practices when taking these is you want to be as perpendicular to the leaf surface as possible, ideally about 10 to 12 inches away. I know that on my Fluke IR thermometer, that at 12 inches away, my measurement diameter is an inch and a half wide. So I'm using that red dot that the little laser shoots out as a guide, and I'm positioning that right in the middle of a leaf that's at least 1.5 inches in diameter because it's a cone that's being measured, not a little laser point. So the further you get away, the bigger that cone gets. The closer you get, the smaller that cone gets.
Yeah, there's more than what you're seeing with the naked eye if you're using one of those. And we saw that in that new design that Affinity did with that kind of built-in VPD calculator in there. So you actually see the cone.
AC Infinity, yeah,
Yep.
they created a VPD thermometer, which is an IR thermometer that does the VPD calcs for you, which is quite interesting.
Yeah.
Um, but yeah, so you want to do that in the middle of photo period, understand what your measurement diameter is, and then take averages across the room again, maybe every 4 feet, um, and record that data, and then
What do you
overlay
think
it
an
with your airflow
acceptable
data.
range should be? Like nothing's ever going to be perfect, right? So if we're going to map out a room, we're going to dial everything in. I think, to manage expectations so someone doesn't drive themselves nuts. What do you think is an acceptable range from, we'll just talk about leaf temperature for the time being from like, same tier front to back or the delta between the top tier and the front tier? I guess in terms of like is that a 2 degree delta between is that like okay like I'm not in such bad shape, but if you see like a 4 or 5 or 6 degree delta, you've got some work to do.
Well, I typically look at it, I use that leaf surface temperature data to then calculate my VPD more accurately. And then
Right. You're looking at
I
leaf
look at
leaf
the
VPD versus like ambient room VPD.
That's right. So when I'm talking like deviations or acceptable deviations from front to back or top to bottom, I'm looking at it in kilopascals in terms of VPD, not leaf surface, Fahrenheit. And
Hmm.
so, ideally I want to be within 0.2 kilopascals, maybe zero point 0.3, I think is somewhat acceptable. Ideally less, right? Ideally, I'd want it all to be identical. But if I'm
Sure.
within plus or minus zero point 0.2, I think I can handle that,
Yeah, that
right?
makes sense.
And then for leaf surface temperature, assuming that your climate sensors are accurate and calibrated and not being influenced by other things like lights or motors, that you actually have a correct ambient temperature and humidity value, and you're doing the leaf surface temperature readings correctly, you typically are seeing roughly a negative 3 degree leaf temperature offset. So the leaves, that means, are about roughly 3 degrees cooler than the air in the middle of the photo period in a flowering cannabis crop that's transpiring with the lights on. That's on average what I typically see. I've seen it as low as 5 degrees offset. But when your lights are off, that offset's zero,
Hmm.
right? It's the same as ambient. When your lights first turn on, that offset's going to be almost nothing, right? So like let's say if your air is 83 degrees, your leaf surface temperature is probably going to be somewhere around 80. Um, it's nice to keep that leaf surface temperature around 80 degrees or less if you can. That just signifies a healthy transpiring plant. Um, in terms of air velocity, what you would be expecting, again, don't get confused with CFM. That's one thing I often get too, is people want to track airflow in CFM.
Hmm.
Um, that's a volumetric flow rate. So you should think of CFM as airflow within a confined space, like a piece of ductwork, right? Cubic feet per minute versus just feet per minute, which is a velocity measurement, not a volumetric flow rate. So when you're thinking of everything around the canopy, feet per minute or meters per second, which is the equivalent in metric system, be the two values that units of measurement that you're going to be tracking. In a veg crop, you're looking somewhere between 100 to 200 roughly feet per minute. And in, let's say, 1,000 to 1,200 ppfd max flower room, you're looking somewhere between 200 and 300. We're hoping to get better information on the exact optimal values for that in this research trial that we're conducting.
It's interesting that for traditional CEA non-cannabis crops, like that seems to be a lot more somewhat understood. And I think you highlighted for me previously, it's, really around like 100 feet per minute. But it's fascinating that, here you have this multi-billion dollar industry and we don't really know what is the ideal for cannabis. We think it's somewhere between 250 and 300-ish is kind of what I've been heard and told over the last year with you. And it's exciting that PIP and other organizations are getting together to kind of really better understand this and validate it. And so I'm
Yeah.
excited to see what comes out of this research trial that we're doing.
Well, I would also tell people that you don't need to adhere to a specific number. Like the difference between 250 feet per minute and 300 is extremely small, right? So if you're plus or minus, let's say your average is 250, but you're getting readings at 200 and 300,
And you're
that's
probably good.
you're
Yeah.
totally good. I mean, because like you'll watch I've taken thousands of these readings at the canopy. I mean, thousands of airflow readings, and it fluctuates. Airflow can be a little bit challenging at times. And so that's why by collecting more data and getting room averages and row averages, you get a better idea of where you're sitting at. And then looking at those readings and seeing. But that also means those stands and collecting good data, the right height is more important because you get better accurate data. But so if you see fluctuations, 50 feet per minute is really not that much. So we're talking pretty tight ranges. I wouldn't try and control it to an exact number. I would try and keep it within a range, you know?
Sure, that makes sense. And but at the same time too, if you're for some reason you're like, man, I'm at 500 feet per minute, you know that you got to dial some stuff back. But if you're at 50 or 100, you know that you've got some room to improve upon. And I think you're
Yes.
really looking for some level of consistency. I know you're
Yep.
taking averages, but I think consistency is key. That seems to be an ongoing theme for all cannabis production. Is like, how well can you do this consistently?
Yeah.
Uh,
Well, and so like back on those what's the ideal range? Most greenhouse designers, they try and target an airflow rate of 100 to 200 feet per minute across the top of the canopy, or zero point 0.5 to 1 meters per second, roughly. And the hypothesis currently is that cannabis is such a higher light crop. It takes in such a higher ppfd than most commercially grown greenhouse crops. I mean, leafy greens are in the what, 3 to 400 range.
Yeah.
Peppers are
I mean,
like in the
like I think
600 range.
peppers are 600. That's about as
Yeah.
almost as close as you get.
Tomatoes and peppers are two of the
Tomatoes.
higher light crops that you typically see, but even those are less than 1,000 in terms of their ideal, ppfd. Um, Cannabis is often grown well above 1,000, 1,000 to 1,200. And so that is where the hypothesis of the higher airflow rate is that it's taking in more light energy, so it needs a higher airflow rate to balance that energy balance and heat transfer in the leaf.
Hmm. I'm going to ask you a question that I don't want to call it like hippie folklore, but maybe more of like a traditional approach that maybe someone has done in the past. I know I've thought about it. Is there any value in like utilizing dry ice to create essentially smoke or fog to get a visual aid sense of how HVAC and airflow in your room is moving? Do you see any advantages or reason to do something like that? Because that's another really uh, economical way to get a sense of how airflow could be moving through your facility.
Yeah, I wouldn't do it with plants in the room. I would do this at startup and commissioning to do a smoke test. But absolutely, I probably wouldn't use dry ice. There's devices that firefighters use to simulate fires. It's a little box you plug in and you fill it with a fluid, and you turn it on and it produces a pretty intense smoke cloud, and it's not a harmful smoke. I've seen those be used quite a bit. I've never done it myself, but I believe you can even rent them. But it's essentially a fog machine
Hmm.
that puts out a high amount of fog, and a dense fog similar to like fire smoke. And yeah, firefighters use it in training all the time. I've seen people use them in greenhouses and in indoor settings to test airflow. But it's a qualitative assessment, right? So what else is it? You walk around that room with that smoke in it, you're now influencing how it trails. So like, how are you actually learning from it? Um, yes, I think it can be useful, but to an extent.
Yeah, yeah. I've never done it for that reason. I like the idea of it. Maybe visually it could be neat, but I don't know how to quantify it, and I don't know how to take, I guess, what you observe and turn it into something actionable per se. And maybe that's only because I've never done it.
That's
I
very
guess my
similar to the CFD modeling though too, is like that's kind of what you get is you get these line traces through the room of air
Mhm.
velocity and color, and you get to visually see how it moves, the air fluid moves throughout the room.
I guess the other one too, and it kind of comes from, like the automotive and aerospace kind of space and you know, is there any value in hanging essentially streamers from, let's say, the top of your lights to see what streamers are moving? They do that a lot with like aerodynamics with car building and stuff like that, and kind of see what's flapping and what's not flapping or things like that.
The only
It
reason
seems like a huge pain in the ass to do something like that.
Yeah, I mean, I don't know. I think I wouldn't really recommend it. The only value I see in doing something like that is it's a quick visual cue to see if your fans are on or off. So, especially in these multi-tier rooms where you have all these in-rack airflow fans at the front of your room, sometimes it's
Hmm.
hard to tell when they're on which ones are not on, with a quick visual. And so the only reason I could think of using a streamer is a quick check to see if the fans are operational or not. But that should be a room check thing anyways, every day as you're in your morning walks and your evening checks before the lights turn off is make sure the fans are on. And
And
one
then,
one other quick tip though too is like, as you're doing your room walks, just check to make sure your fans are on and the air's moving through the racks. Um, Interestingly enough, the back of your hand has the most receptors for identifying airflow at low velocities than anywhere else on your body. So if you're going to try and check airflow, use the back and the top, like the top of your hand. So that is by far the most sensitive area to detect really low air velocities.
Because naturally, most people put their hand like this, right?
They put their hand like this, but you turn it over and you actually feel it so much more on the back of your hand.
Yeah. I've seen like the HVAC guys like lick the top of their hand, which I'm not encouraging. But yeah, lick the top of their hand and then kind of put their hand underneath to get a feel for that. I guess my last question, because I know I was actually surprised. I thought this was gonna be like a 20 or 30 minute kind of thing, and we're burning like an hour here. But again, this is if you're trying to fine tune your facility, get the most out of your yield, get the most out of your quality. This is something that is just not talked about enough. And it could be something that's holding your facility back. Um, my last question today is going to be, is there any value in doing all of these airflow readings and leaf surface temperature readings with your in-rack air circulation turned off? So you're just looking at what your HVAC is doing alone and then duplicating it with it on. Is there any value analytically from that?
Not that
Because
I can
obviously it's
see.
because obviously it's double the work. So if you're not getting
Well,
double the benefit, I would question doing it.
I think you design your room with the assumption that your in-rack airflow systems are always running.
Mm,
So, so it's I don't see much value in shutting it off and seeing what you get because in normal operation, you're not going to shut those fans off, right? That does remind me of one other point though. With our new VAS 2.0 airflow system, it's putting out over double the amount of air 3 feet below the duct that the original system did. So it's putting out a significantly higher air velocity further down with a further throw into the canopy. We have data at the duct 1, 2, 3, and 4 feet below every 2 feet for every single configuration we would ever sell. So we know how that system will perform and how far it'll penetrate, what velocities it'll produce. Um, why did I just totally blank on what I was getting to? Sorry.
that's okay. No, you bring up a good point though, because while you're
Oh,
thinking about
sorry. I
got
sorry.
it, there you go.
I got it. So with that being said, because it produces so much more velocity, you might now for the first time you have a system where it makes sense to vary your fan speeds. In the past and all of the ones I've ever used, we always just ran our fans at 100% all the time and never changed them,
Yeah, but you
right?
wanted like 130 or 150%, right?
Right. And so now with 2.0, working with a lot of our growers, especially the ones we were beta testing the system at in development, we were finding the need for varying it much more. Essentially, when the plants are young and right, flipped from veg and they're a lot further away from the lights and the ductwork, you're running your fans at a higher speed to get that penetration and velocity in that 100 to 200 feet per minute. But let's say you finish your plants at 6 inches away from the lights. That means your ductwork is maybe 6 to 8 inches away from the top of that canopy. If you had those fans with this system now on 100%, you're producing way more than 300 feet per minute, maybe even close to 800 to 1,000. So you're going to have a need to turn it down, and that's cool to me because now you can actually now dial in your airflow to what you want in that range. It's a tool now, not just something around 100%. So when you're taking these measurements, I would also record the fan speed for VAS 2.0. I would say, am I running my fans at 100%? You
Yeah.
know,
And that's something that Pip, utilizing our incredible sales team and how connected they are to growers and the feedback they're getting, and then paired with our in-house engineering team, we have a really good ear to our customer. And then having folks on the team like you, me, Jesse, Hunter, that do have that cultivation background, Darren as well, James, we're out there and we're listening and we're asking these questions and we're taking this back to our team. And now Pip has solved a problem of everybody always wanted more airflow than a lot of the traditional solutions could give. And they were running everything at 100%, not just 100% wanting more, but also 100% of the energy load too. And so now what we've created is something that if you need to run it at 100%, you have the ability to for those periods of time like you're talking about, where you have maybe a 4 foot distance where your plants are smaller when they first come in. You're just trying to get to that right. But most people are dimming down quite a bit. It could be maybe they max out at 75%. I think we have a couple growers that are at 50%. And so now their energy consumptions and consumable is actually lowered as well. So it's
because there's an
pretty neat
EC
that,
motor in the fan. So that, yeah, the EC motor allows you to save power as you run on partial speeds. And it's good. You're saving power and you're getting the airflow your plants need.
now on that note too, the big differentiator there is like that system that we've developed is really you have two fans at the front of your rack. And that carries a lot of value versus having, because not only is the airflow balance for the distribution of it, but traditionally what we see is if someone has I don't know, a 48-foot rack or longer. They're basically adding a fan and electrical distribution to that fan, sometimes every 8 feet, but a lot of times every 16 feet down that
Hmm.
row. And so they have multiple fans. And what ends up happening, as we were talking about earlier, that kind of industry vernacular of wind burn. You have a lot of wind or high velocity airflow right at the front, and so it's negatively impacting those plants. And then the ones that are behind it are getting significantly less. And so you
Yep.
create, our goal was to create uniformity and give you more, um, I don't want to say CFM now. I want to say feet per minute.
Velocity.
Velocity, thank you. I want to get it right.
Yeah.
There's a lot of interesting lingo with air quality and airspeed. But that being said, we've now produced something that gives you more than you need, that you can dial down on a 0 to 10 volt essentially to exactly where you need to be. Versus a lot of the fans out there don't have, if they have speeds, it's three speeds. It's low, medium, and high. And a lot of them don't have speeds. And I go to facilities, I'm like, hey, can you let's just turn that speed down a little bit. And they're like, we can't. It's either all or nothing. So kind of something to be looking out for. And if you haven't explored the new VAS Gen 2 solution, it's definitely worth looking into. And we have a ton of data to support kind of how we got to this design.
Hmm. Yeah. Well, man, I think that was a good one. We probably talked a lot longer than we were planning on it, but I spend so much time on airflow and climate and all this stuff that it's easy for me to dive down the rabbit hole. So
Yeah, but if it wasn't
appreciate
important,
people bearing with us on this one.
no, I mean, look, if you're struggling in your facility with botrytis consistently in certain areas, you're seeing some inconsistencies in your crop, or even maybe you think it's something that's nutritional, as we highlighted earlier, it might be none of those things. And airflow might be that one thing that's holding you from going from maybe a B plus quality cultivation facility to like, an A or an A plus. And so, I think it's an important topic and there's a reason it went this long. But yeah, again, we want to thank our listeners, and thanks to Pip for sponsoring this stuff and not having any weird ads or anything. As if you're not following us on Audible, LinkedIn, I don't even know what I'm saying, YouTube, all the
Spotify.
things, click it, like it, smash it, subscribe to it, all that fun stuff. Anders, pleasure as always. Thanks for being such an educational resource for our team and also for our customers and our listeners.
Yeah. Thanks for everyone listening to Michael. It's always a pleasure, man.
Talk to you soon.